Hi, in this video tutorial we are going to model above ground biomass density using the GEDI L4A dataset, Sentinel-2 imagery, and vegetation indices derived from the Sentinel-2 imagery. So these vegetation indices are the normalized difference vegetation index, the canopy chlorophyll content index, the specific leaf area vegetation index, and we are going to use a random forest model here. So I've already prepared the training dataset for this video tutorial. So please check the following YouTube video tutorials that I prepared for showing you how to prepare training data for above ground biomass modeling. So the first tutorial is part 1 here using GEDI, and then we have the part 2 combining with the Sentinel-2 imagery. Okay, right. So as usual, we are going to start by installing the libraries that are not pre-installed in Colab. So we are going to install here Rasterio and EarthPy. So these libraries are important for handling the satellite imagery. And then next we are going to import all the libraries that we are going to use for this tutorial. And then following that we are going to set up a Colab. So first we mount our Google Drive. So the Google Drive here is where my the datasets are stored. That is the training dataset. So this includes the above ground biomass dataset that I created in the previous tutorials in Google Earth Engine, and also the satellite imagery and the derived vegetation indices. Right, once you have access to your Google Drive, now we come here where we access the datasets. So here first we are going to define the predictor and the target variables. So the predictor variables, so we have our Sentinel-2 bands plus the vegetation indices. And for our target variable, it's above ground biomass. And this is the sample path where we have the sample training dataset containing the above ground biomass and the predictors in .csv file. And then we also have the path where we contain our imagery. So this is a stacked imagery containing the Sentinel-2 imagery and also the vegetation indices. So this is in GeoTIFF format. So let's visualize the Sentinel-2 imagery to check if everything is okay. So this code just shows you how to load the imagery using the Rasterio library. So here is the example of the imagery of the study area. So this is displayed as a shortwave infrared. So this is a band 12, Sentinel band 12, and the near infrared band 8, and then the red which is band 4. Right, so we can see that here the green color shows the forest area, while the other colors this showing the non-forest area. Right, next we are going to import the datasets that contains the predictor variables and the target variable. So this is the CSV file. So here we have our predictor variables from Sentinel-2 plus the vegetation indices derived from Sentinel-2, and here we have our target variable, which is above ground biomass. So next thing that we are going to do, we will split the dataset, the sample dataset, into the data that is going to be used for training the model and the data that is going to be used to test the model or validate the model. And as you can see here, we have 80% of the data is going to be used for training the model, while 20% is going to be used to test the model. So here are our data set. So we have for the training features. So the training features, we have 3,626 points, which shows the Sentinel-2 bands plus the vegetation index. So these are 12 features. And then we have the test features, which is 907. And then we also have the same number of features. And then for the train label, this is simply the target variable. So in this case, the above ground biomass density. So we have only one here, since we are only targeting the above ground biomass density. So remember, this is a regression, not a classification. Right. And then next we are going to perform exploratory data analysis in order to understand our data set before we build a machine learning model. So this is very critical. So we are going to use here the pandas library in order to do the data manipulation. In this case, we want to build a data frame, okay, so containing our training data set. So we are going to define here the predictor variables in the training data set. So this is the Sentinel-2 bands plus the vegetation indices. And then we have our target variable y, which is the above ground biomass density. Right, so if we check the first 5 rows, we can see that this is our predictor variables from the Sentinel-2 bands and the vegetation indices and our target variable, which is above ground biomass density. And then if we check the data further, we can see that all the data sets here in float. So our data set is fine. And then next we want to check the summary statistics. And then if we check the summary statistics here, we can see the mean, standard deviation, minimum, the quartiles, and the maximum. But it's quite difficult to understand the data set. So we are going to visualize the data sets using graphs. So here we are just going to use the box plot to visualize our data set. Again, we are just going to visualize the median, the quartiles, and potential outliers. So this is the distribution of the data set across all the features that we are going to use for the model. So as you can see, we have a number of outliers in the Sentinel-2 bands. Interesting, for the vegetation index, we don't have any outliers. Right, so next we are going to select and train the model. So for this case, we are going to use to use the random forest regressor. So this is a random forest regression model that we use in order to model above ground biomass. So what are we going to do? So we would like to tune the hyperparameters of the random forest model. So what are we going to do specifically in this code? So first we are going to set the random seed. So in order to have reproducibility, this means that if we run this code, we get the same result. And then we are going to define a parameter grid, okay, for the random forest regressor here. And we are going to use the grid search, okay, GridSearchCV, in order to perform a 5-fold cross validation, okay, so that we find the best hyperparameters. So this is based on the negative mean squared error. Okay, so after fitting the model to the training data, we will try to retrieve the best parameters that is found during the grid search. Right, so note that here we talk about parameters. So remember that parameters are the internal variables of the model that are learned from the training data. For example, just think of weights and linear regression, or the splits in the decision trees. And when we talk of the hyperparameters, remember we are talking about the hyperparameters. So hyperparameters, these are the external settings that control the random forest model learning, that control the random forest during the learning process. So this must be set before the model training. So for example, these N estimators, maximum depth, minimum split, these are the hyperparameters that we want to set. So we set this before the training. Okay, so right. So what is the N estimator? So these are just the number for the decision trees. So we will start from 50, we have 100, we have 200. So we want to get the best estimator. And then the maximum depth. So this is the maximum depth of each tree. And then the minimum sample split. This is the minimum number of samples required to split an internal node. Remember, when we talked about the decision trees and random forests in previous videos, we talked about the number of samples required to split each node. Right. So why do we need this tuning? Why do we need to tune the parameters? So this is very important because if we have too few trees, then we are going to have a bias, and then we are going to experience underfitting. So if we have too many deep trees, that is we have a high maximum depth, then we are going to have a problem of overfitting. And also we have to be very careful about the minimum sample split, because if we have a low number of this, then we are going to have a complex trees, which is not good for our model. Right. So after preparing this, preparing the hyperparameters, then we go to the next step. So here we are going to, this code is just going to use the best parameters that is acquired from the previous code here. So acquired from the grid search. So if we get the best parameter, this is the one that we are going to fit to the training data. Right. After that, we are going to use the k-fold cross validation in order to split the training data into 10 subsets. So these subsets, they are called folds. So this is going to give us an idea of the model performance, right? So we are going to print here the RMSE score, so the root mean square error, right? So from this code we see that the lowest error that we have here is around 18.78. So 18 is just this measurement is for the above ground biomass in megagrams per hectare. Right. After that, we want to plot or want to create a scatter plot for our model, so that we check how the model has performed. So here we are interested in three metrics: the mean bias error, the root mean square error, and the error squared. Okay, so once we run this model, we get these statistics. Okay, so we can see that the mean bias error is showing us a slight systematic over prediction. So this is a positive bias. So this means that the predictors on average, okay, above 0.58. So this is about 0.58 higher than the actual value. Okay, so this is higher than the actual value. So here we have a over prediction that is happening here. In this case, sorry for the mean bias error. And then for the root mean square error, the RMSE. So we have a prediction error here of about plus or minus 20. So this means that the typical prediction error is just ranging plus or minus 20 megagrams per hectare. Okay, so this suggests again moderate inaccuracy. We would like to have a lower number here, which will be much better. So 20 megagrams, yeah, it's a bit megagrams per hectare. It's not good, right? And then the R squared here is again 0.50. It's not terrible, but this means that there's just a room for improvement, because it means that the random forest model is only explaining 50.6% of the variance in the target variable, so not doing a good job. Right, so there's room for improvement there, as I've said. So that means first improving on the above ground biomass density points, check if there are some errors, or even improving on the predictor variables. Right, after that we want to save this model so that we can use it for future prediction or for deployment if it is a good model. But in our case, we want to use this model in order to try to understand how the random forest performed. So we want to run explainable machine learning techniques using SHARP, so that we check we gain insights into how the model performed. So here again we're going to use the joblib library. So remember, I talked in the previous lecture about the joblib library. So this is a very important library because we can use it to save and load Python objects, especially machine learning models that are trained using the Scikit Learn models or Scikit Learn models available in the Scikit Learn library. Right, so after this we are going to predict above ground biomass, and then we're also going to display the above ground biomass map. Okay, so this is simple. Again, here we are just going to load the image, the stacked image that contains the Sentinel-2 bands plus the spectral indices. So these are 12 bands. So 9 Sentinel-2 bands plus 3 vegetation indices. And then we are going to do the reshaping. We perform a prediction using the best random forest model, and then after that we again reshape them to 2D, and then we can display the above ground biomass map. So this is our above ground biomass map. Okay, so please ignore this part. This is just a problem with the visualization. So we were focusing here on these parts. Right, after that we are going to save the map in Google Drive. So you can download this map from Google Drive and then display it in your favorite GIS software. Right, so this was all about this tutorial. So it's just showing us how we can model above ground biomass using GEDI, Sentinel-2 and vegetation indices. and also a random forest regression model. So we have done all this using the Scikit Learn library. Right, so remember, the most of what we're doing now is using Scikit Learn library, so that we can try to use most of the modules that are available there to improve our modeling or classification tasks. Right, so this is all about this tutorial. So I will see you in the next tutorial, where we are going to look at explainable machine learning.